We have Amey Bhangale today from UC Riverside. Amey has been doing a long line of works on variance approximation and specifically on satisfiable instances. There's papers 1, 2, 3, 4, 5, I don't know how many. 6?
7.
7, okay. And so he'll tell us about some of that.
Thank you Eric, for inviting me here to give a talk, and thank you for the introduction. So today this talk will be based on this long-term project of approximately satisfying constraint approximately solving the constraint satisfaction problems, and this talk will be based on multiple joint works with Subhash Koth, Yang Liu, and Dor Minzer. So since this is a discrete math seminar, I'll just start with the main analytical question that came up while studying this this algorithmic problem. So imagine or consider a distribution mu on sigma cross gamma cross phi. Think of sigma gamma phi as finite size sets, say size 2 or size 10. Okay, and let's say you have 3 functions f, g, h, n variate functions that are one bounded, and the 3-wise correlation of f, g, h is large given by this expectation. Okay, so the distribution mu to the n is a product distribution where in every coordinate xi, y, zi you sample with respect to mu independently across every coordinate. Okay, and then the main question is, if you just know that the 3-wise correlation of f, g, h is large, then what structure can you deduce about the functions f, g, h?
So just suppose we had 2. Instead of 3, we had 2. Is it obvious? I mean, we start with 3 for a reason, but
so we for 2 some results are known for distribution for 2-ary correlations, and we started studying 3 because that's the first non-trivial case for constraint satisfaction problems.
Yeah, but what will be the answer for 2?
For 2, I guess so I think something of this sort is known. If the distribution mu is connected, if the support of the distribution mu is a connected graph, then this is large only if these are low degree functions. Yeah.
Low or close to low?
Or close to low degree, yes. Right.
Okay, so you want something similar also.
Yeah, so we want something similar here. Yeah. So
just say, who did it or where was it done?
So this is by Mossel. Yeah. He said that if the distribution is connected, then the only way this expectation is large is if these are like close to low degree functions.
And all this traces back to analysis of Boolean functions developed for inapproximability.
Yeah.
And the case of 2 is the most studied.
Right. And even the question makes sense for 4-ary, 5-ary, and so on. But at this point, we still don't have answer to 3-ary. So that's why. Okay, so one example to keep in mind is mu is just mu is a distribution on fp to the 3, which is supported on arithmetic progressions, like the tuple a plus b, and a plus 2b. In this case, the mu to the n corresponds to arithmetic progressions in fp to the n. And what about the structure? The structure could be of any form, like maybe f has somewhat low complexity, a structure of that sort. For example, f is correlated to a low degree function, or f is correlated to a simple looking function like the function that is shown here, which is a product of individual functions on each coordinate. Okay, so we are looking for such a structural theorem if we know that the 3-wise correlation is large. Okay, so in this talk, I'll discuss how this question arises in approximability of CSP, like in designing algorithms. And I'll also discuss how this question is useful in proving results in additive combinatorics and complexity theory. Okay, so here's a big picture about the project. So we use this inverse theorem, which is basically answer to this analytical question for specific distributions mu. We use these inverse theorems to design algorithm or study complexity of this problem of satisfiable CSP, which I'll define later in this talk. And using these inverse theorems, we proved new results in additive combinatorics, including the restricted 3-term arithmetic progression, the density Hell-Hewitt theorem for the base case, bias linearity testing and direct sum testing. These are like results from proper testing, and then multiplayer parallel repetitions for sum gain, which is a result in complexity theory. So here's the outline of the talk. So I'll first go over the implications of these inverse theorems. Just mention what we show in for these problems, and then I'll start with the main project, the CSP and approximability. And then if I have time, I'll try to connect the answer to the analytical question that I mentioned earlier to a few of these applications. But let's hope I get time to do that. So any questions so far? Okay, so the first question is on density Held-Schmidt theorem. So what is the problem? So consider the set k to the n, and a commutator line of length k is of this form. So there are like k strings. So here I'm representing a commutator line in 3 to the n, which is a set of 3 strings, where in every coordinate you either see the same digit or you see 0, 1, 2 in that order. Okay, so the predicate that corresponds to this DHA3 is this predicate. So either you see all 0, all 1, all 2s, or you see 0, 1, 2 in that order. Okay. And the question here is, how large can a subset of k to the n be to avoid any commutator line of length k? Okay, and so this is related to the density Held-Schmidt theorem is related to the Held-Schmidt theorem, which says that if you color k to the n with few colors, then there has to be one monochromatic combinatorial line. And the density version refers to the even stronger version of such a statement. Okay, so in 89 and 91, Furstenberg and Katz-Nelson in their influential work, they show the density version of the Held-Schmidt theorem, which goes as follows: that for every integer k and density delta greater than 0 constant, for sufficiently large n, if you take any subset of k to the n of size delta times k to the n of density at least delta, then that set must contain a commutator line of length k. Okay. So this proof is based on some ergodic theory. So I don't know much about this proof, but so no quantitative bound on delta was given. For example, can you take delta to be 1 or log n, or 1 or poly n, 1 or n to the epsilon, for example. Okay, and this theorem is quite useful because it's one of the sparsest predicate for which you ask such a question, and because of this, you can show the Zemerides arithmetic progression theorem using just the density version of the Held-Schmidt theorem, as well as some multidimensional version of the Zemerides theorem. So these theorems they follow easily from the density Held-Schmidt theorem. And there's a lower bound known, which is based on the Behran's construction, the same lower bound for arithmetic progressions, which is of this form. And in 2012, in a collaborative way, led by Gowers, they gave a first quantitative bound on the density delta. They showed that if delta is inverse iterated logarithm of n, then any set with this density must contain a commutator line. Okay, and this result worked for every k. So this bound was true for every k. What we show using one of our inverse theorems is that we gave a reasonable quantitative bound on delta. So we showed that any set of density 1 over 4 log n, poly 4 log n, of 3 to the n, if you take any set with this density, then it contains a commutator line.
Only for 3.
Only for 3, yeah. So our theorem works only for the 3 to the n. And it's open for 4 and onwards.
And the reason is that you analyze 3 functions and not more than 3?
Yes. So one of the reasons that we could only get to 3 is because we could answer the analytical question for some distributions, which is on 3 array things. And if you can answer the same question for 4 array and onwards, that would be helpful in answering this question for larger k. Okay, so that's the first application. Let's look at the second application. So it's about the 3-term arithmetic progression. So again, the same question here. Fix a subset of fp to the n And then an arithmetic progression in FP to the n is a tuple of the form x, x plus y, x plus 2y. And you want y to be non-zero because otherwise you always have arithmetic progressions in any subset. And then the same question, how large can A be to avoid any three-term arithmetic progression? Okay, and there is a long history of work in the integer case, which is like if you take for large enough f, and if you take any subset A of the numbers 1 to n with density at least delta, then it contains a non-trivial AP, 3A. Okay, and there's a long history of work, and recently Kelly and Mecca, they gave a bound on density which is closer to the actual answer. And the same question in finite field also received much attention. So Roth and Mechelon, they gave a bound of 1 over some m to the c, where c is some constant between 0 and 1. And later, Batman and Katz, they improved this poly to something, the exponent to something greater than 1. And recently, using this method called the polynomial method, Ellenberg and Jiswajit, they gave an exponentially small bound on such a set. Okay, so that's the state of the art for, and yeah, that's the state of the art for three-term arithmetic progression. So what we study instead of like general 3AP is something called restricted three-term arithmetic progression. Okay, so let's fix a subset S of FP, not FP to the sun, just FP, and a S restricted three-term arithmetic progression is of the form x, x plus y, x plus 2y, where y is from the set S to the n. So we restrict the shifts from the AP. Instead of the shifts coming from any element from FP, we restrict it to coming from just the set S. And then you can ask the same question. So Hasla, Hollenstein, and Mosel, they ask this question that if you restrict your shifts to come from 0, 1, then how large can A be to avoid any restricted three-term arithmetic progression? And the same result, the polymath result for the density Hell-Hewitt theorem, it implies a similar bound on the density of such sets. So in the iterated logarithm of n. And we show initially in 2023 that if you restrict your shifts to 0, 1, 2, while not answering the original question, but if you increase your shift set to 0, 1, 2, then you could get a reasonable bound on the sets avoiding such restricted three-term arithmetic progressions. So here it's like 3 logs of it. And very recently, we answered the original question of Hasla, Hollenstein, and Mosel, where the shift is only coming from 0, 1. Okay, and we get the same bound there. Any questions? So the next two applications are about property testing. So linearity testing. Here the setup is
the better low bounds for the restricted case better than Barron?
No, I think it's similar as the Barron's construction. So there's still long gap between the lower and upper bounds. Okay, so linearity testing, given a Boolean function from 0, 1 to the n to 0, 1, you want to decide if f is a linear function or f is far from a linear function. So there's a very natural test that you sample two inputs x and y uniformly at random independently and check if f of x plus f of y is equal to f of x. Just the property of a function being linear. And of course, every linear test, linear function passes the test with priority 1. And since we are working with the Boolean alphabet, a random function passes the test with priority half. So half, any like a random function passes with half, so function with no structure passes the test with priority half, and linear function passes the test with priority 1. Now, here you can ask two questions. One is in the 99% regime, that if a given function passes the test with priority, let's say 0.9, very close to 1, 0.99, then can you deduce that f is close to a linear function? That's called a 99% regime. And here, Blum, Luby, and Rubinfeld showed that that's true. So if a given function passes the test with priority 1 minus epsilon, then f is indeed correlated to a linear function. And the harder regime is the 1% regime, where you ask the same question, but the condition is that the function passes the test with priority better than a random function. So half plus epsilon, like 0.51 or something. Okay, and here Bellari et al. Showed that this is also true in the 1% regime. So if the function passes the test with probability better than half, then f must be correlated to a linear function. Okay. Now, what we study is the bias linearity testing. So again, the same setup, but you just want your input queries to be coming from a p-bias distribution. Okay, instead of like a uniform distribution. Okay. So for a given fix a parameter p, say 0.4, and you want all three queries to be, or all, if you query your function at 4 points, all queries to be coming from the p-bias distribution. And such p-bias distributions are important because they are used to study sharp threshold behavior in graphs. They're also useful in many hardness of approximation results. So the question is, can we get a p-bias linearity testing? And here, Koperty and Saraf in 2009, they gave a constant query test in the 99% regime. So for every p, there's a test that queries some constantly many points depending on the parameter p, independent of the parameter n, such that if the function passes the test with probability 1 minus epsilon, f is indeed correlated to a linear function. And Irith, Filmus, and Harsha, they gave a four query test in the 99% regime. So they improved the query complexity of this test from arbitrary constant to just 4 queries. In fact, the result is more general. They gave a 2 to the d plus 1 query test for checking degree d functions. Okay, and yeah, what we show in this in one of the papers is that we have a bias linearity testing result, but in the 1% regime. So fix for every delta, fix the bias parameter between 1/3 and 2/3. Then there exists a 4 query p bias linearity test with perfect completeness, and the soundness is half plus delta.
Wasn't there the 3 query test with a bunch of authors, Kindler?
I cannot hear you. I don't know if others can.
I'm asking about some older paper.
So yeah, I think there is a paper where the queries are. So I think maybe Iri's question is there is some other paper related to this p-bias testing, maybe by Guy Kindler. So I don't remember the paper, but I think are you talking about a problem where the queries are coming from a slice of a hypercube?
Yes.
Yeah. So there was one paper where you have a function which is only on, let's say, the pn slice of the hypercube, and then you can also define closeness to a linear function and all. It's not on the whole domain. And then there's a test for that.
But I mean.
But that was in the 99% regime too.
Right, but I mean, it just happened to be on the slice. It could have well been on the p-bias cube.
Right. Yes. Yeah. Sorry, I mean, I missed the reference, but I should have added it.
So
but
we know that the natural 3 query test does not work.
So I think you can't have a 3 query p-bias test, natural test. You need to have like 2 points and the addition of 2 points in the query set.
No, I disagree. Sorry. In that paper, the distribution was to choose 2 pn number of bits out of the n bits.
Right.
And on this set, you do a regular BLR test.
Right.
And you get 3 queries that are all p-bias distributed.
Right.
And
I see.
It works. So.
Okay.
Yeah.
So I take it back. So on the slice, if you have a slice on Pn, so you go to a subset of size 2Pn, okay, and only do sort of BLR test there. So on that restricted set, using BLR, you get that the function is correlated to a linear function. So you get such a statement for most subsets of size 2Pn, and then from that you put it back to the full global set. But that test also works for in the 99%. Yes. So you can only show. I mean, the result is if the test passes with probability 1 minus epsilon, then f is correlated to.
But you don't know how to rule out the 3 query test for the 1%.
Right.
Okay.
Yeah.
Also here, you only get it for a very specific range of p. You would hope to get it for p going to 0.
Right. So this is a paper. So I think there's a paper by Subhash and Kunal, where if you go anything beyond this, the p, then you don't get this conclusion that f is correlated to a linear function. You have to do something more. Correct me if I'm wrong. So there the
So we can
conclusion
show
is,
that the natural test that you said, like where you take two PN coordinates and do the BLR, so that fails.
Meaning,
So that you can find a function which is not correlated to any linear function, but it passes the test with probability like more than like half plus epsilon. But like for every P, you can find a range, like you can get a query complexity of some kind of test. Like you need something like 1 over P queries.
and this function that causes the test to fail, it has no structure or it has some?
no, I think it has. I think the conclusion is that, so again, so I'm just quoting from what I heard, that if there is a 4-query test where P is outside of this range, and if the function passes the test with probability half plus delta, then the function is correlated to a linear function times a low degree function.
Okay.
So you don't get correlation with the linear function, but linear times some low degree. In some sense, I haven't defined what low degree means, but so the conclusion differs in the regime which is outside of this. And I think maybe for 3-query P biased, the same behavior holds. Is that true? Or?
Yeah, I think it's only for like a certain kind of test. It's like if you want to do a BLR-like test, whatever that means, like you can say that there are functions which pass the test with probability half plus epsilon, but which are not correlated to any linear function. Like
Right,
if P is outside this range, for example. But it is correlated to a linear times a low degree thing.
Right. So I think this is true that if you want a conclusion to be this, then 4-query is the minimum sort of in the 1% regime. So I mean, there's an asterisk there.
This whole counterexample is only for 3 queries and not for 4 queries?
No. So it says, for example, that if P is not in this range, then certain kind of tests you need at least more than 4 queries. And similarly for every such range.
Okay, so
like for example, it says that.
So for 4, what he said is that this test works in this range. If you go outside, you need to get you will get a weaker structure, and that is needed. You can't just get a correlation with the linear function. Now you have the same question for 5 queries. So what Kunal is saying is for 5 queries, there is a different range of P for which the same conclusion holds. And if you go outside of this range, you need to go to a wider class of function, which is linear times low degree. For 6 queries, the range will be different. But for 4 queries, this is the tight range. And if you go anything like anywhere beyond this, your conclusion will differ. And this result was shown by Subhash and Kunal. Yes, question.
How are you measuring distance here? Is it with respect to use of P, or is it like?
With respect to use of P, that's the natural way to measure the distance. Okay. So the 4th application is the direct sum testing. So here you have a function from an arbitrary domain sigma to the n to fp, and consider this diamond test. Okay, so you sample 2 inputs uniformly at random, call it A and B. Sample a random subset S of coordinates, and you sort of mismatch these A and B's, okay, to get 2 other queries. Okay, so I have just drawn a picture here. So let's say you have 2 queries. The first 2 queries are A1 to A5 and B1 to B5. Okay, and let's say you ended up sampling a subset which is 3, 4. Then the 3rd query is you just swap the 3 and 4th coordinate of A with the corresponding B's that you got. Okay, and the 4th query is you do the opposite. So so you only sample 2 random things, and they give you the later 2 queries, and then you test if f of AP, and so f at this point, minus at this point, and minus at this point, they sum to 0. Okay. Now, why am I looking at such a weird test? Because if f is a direct sum function, which is of this form, it's sum of individual functions on each coordinate, then such functions, no matter what this fi is, they will pass the test with probability 1. Right? Because you are just summing up these individual things like this to get f at those points. Another way to do the sum is coordinate wise like this, because this direct sum, and then you see that you have 1 copy of A1, 1 copy of B1, positive, and then the same with negative sign. Okay, so coordinate wise you get 0, so overall you get 0. Okay, so this is a natural diamond test. This was, I think, introduced. This was introduced by Edith and Golubov to And they conjecture that this is a proper test to check the direct sum function like this. Okay, in the 99% regime. Okay, again, it means that if a given function f passes this test with probability 0.99, then f must be correlated to a direct sum function. And this was answered positively recently by Westover, Yu, and Zheng in the 99% regime. And what we show is that this test works in the 1% regime. So if the test passes with probability 1 over p plus epsilon, then f is correlated to a direct sum function. And there's an asterisk here because, as I said earlier, similar to the p-bias linearity testing, here you can't hope to get a conclusion which is simply just a direct sum function. So you need to introduce some low degree functions also. So, okay, but other than the technicalities, it was known in the 99% regime, and we showed that it works in the 1% regime. Okay, and the last application is to parallel replication. This slide is a bit dense, so yes, but I'll just say what it is. So consider a 2-player 1-round game. So there's a verifier and there are 2 players. The verifier samples a question, sends it to one question to Alice and another question to Bob. The verifier gets back the answer from these 2 players, and then based on the question and the answer pair, the verifier decides to accept or reject. Okay, so that's a 2-player game. I have written here in a more formal way, but maybe we don't need that. And you can define a value of a game, which is the maximum probability with which the player convinces the verifier to accept. Okay, so not every game. So no matter what strategy they decide to play with respect to, that's what is the maximum probability with which they can make the verifier accept. Okay, and they're not allowed to communicate once the questions are sent. So that's the value of the game. For at least for hardness approximation result, it's important to amplify the gap of this game. That if it's important to get a game whose value is like very, very small. And one natural way to reduce the value of the game is just to repeat this game sequentially. Just play 1 round of the game. Okay, then once you get back the answer, once the verifier gets back the answer, play the same game and then do it n times. And it can be easily shown that if you repeat it sequentially, the value goes down exponentially then. Okay, but the game is no longer a 1-round game. Whereas for the hardness approximation results, you need a 1-round game. Just send all the questions, get back all the answers, and then decide. And one natural way to play this is just repeat this game parallelly n times. So whatever the verifier is playing, whatever game the verifier is playing, just sample n different questions using the same distribution, send all the questions to the player, get all the answers back, and then decide whether to accept or reject. And the question here is, the main question here is, if the value of the original game is less than 1, then what can we conclude about the value of the parallel repeated game? And this can be generalized to more than 2-player games. So parallel repetition of 2-player game is well understood. So Raz in 98 showed that the value of this parallel repeated game, it decays exponentially with n if the value of the game is less than 1 to start to begin with. And subsequent works, they simplified and improved these parameters from this Raz's result. I want to focus on one game, which is a k-player game, where same setup, the verifier sends question, it gets the answer. Here, the answer set is coming from some abelian group. But then the final predicate just depends on the XOR or addition of these answers that the verifier gets from the players. Because those are called XOR games. I think we defined it to be XOR games. And so this GSZ game, which is a special type of XOR game, which received much attention, this was studied recently, and people try to understand the value of the parallel repetition of the GSZ game. And there, Holmerin and Raz, they gave an inverse polynomial bound. So the value of the GSZ to the n is like 1 over inverse polynomial in n. And this was improved to inverse exponential by Breverman, Koth, and Minzer. And what we show is that for any 3-player XOR game, which is a generalization of GSZ game, we gave an exponential bound on the value of the parallel repeated game. Okay. And again, there's a star here because you need some more conditions on the 3-player game. Okay. And also it only works for 3-player game, not like 4-player. And again, this goes back to the same question that we could only answer the analytical question for the 3-ary case and not 4. So if you could answer those questions for 4-ary, then maybe this can be shown for 4-player.
So the star is about a billion embedding or some kind of.
No, the star is about this game. If you look at the question triples, then it gives you a tripartite graph or hypergraph. It's about the structure of that graph. You need that. If you look at just question pair to player 1 and player 2, then you need that graph to be connected. Just question pair of 2 and 3, you need that graph to be connected. And 1 and 3, you need that to be connected. So it's some technical condition, but yeah, so if I have time, I'll show why that appears somewhere, but so any questions so far?
Do we know that it's not true for general, like that some technical condition is necessary?
No. We could only show it for this. Maybe it's true for all. Sorry, yes. And yeah, so I mean, I did not mention all the works here, but for 3 players, special type of games where the questions are Boolean or the answers are Boolean, these games were studied, and some inverse polynomial bounds are known for certain 3-player games. But I think anything beyond 4-player is not known. Right. Yeah. So the state of the art is for some 3-player games, such a result or something of this sort is known. But for 4 players onward, the question is wide open.
I mean, I guess there is this, if the game is very well connected.
Right, yes, yeah, for K-player, if the game is connected, then such a result is known. This is a result by Irith et al. And we also have another paper where we showed that if the game is projection game, if the set of answers, accepting answers, they have some structure, then it works for every game. There is one small important thing that maybe I should mention is that here it depends on the size of the game. Okay, so here the exponent here there is some factor that depends on the size of the game, whereas the Rajesh proof and all these proofs, they don't depend on the size of the game. The game could be on n variables, or yes. And if you repeat that game n square times, you still get a decay, or n times you still get a decay. Whereas, here the game is, so this decay depends on the game size. And that's also maybe an important question for K-player game, just show a decay without the dependency on the size of the game.
I guess for the GHZ game, it's not important because it's a constant size game.
Right, for GHZ game, it's not important because here the questions are just bits. So verify is only sending 0 or 1, 0 or 1 and 0 or 1. The players are responding back with 0 or 1, okay? And then the verifier does some test. So the game size is finite if you independent of n. So there it doesn't matter. Here also we assume that this is finite, so it doesn't matter. But it's an important question to show parallel repetition for 3-player game that does not depend on the game size.
I mean, it could also be necessary for some games to be.
Oh, is it?
I don't know.
So.
I mean, it depends actually on how much you want it to depend on the game size. So for example, if you want the bound to not depend even on the answer length, then the problem is actually equivalent to the density Hills to it theorem. But if you allow it to depend on answer lengths, like Raje's result also depends on the length of the answers in the game. And so then you could expect an exponential bound or something.
Game size here just means total length of questions plus answers, or
Yeah, so total length of questions, answers, maybe if there's a probability involved, you don't want that probability to be like very, so the bit complexity of describing the game, let's say.
So I mean, if the game is like comes from some preset instance and then you want to do a repetition, then you think of the game as very large and you only do a few times the repetition. In this setting, it's kind of the opposite. The game is something that you think of as fixed, and
I usually think of the game as being small. So
Okay. No, but for the original application, the actual game that you consider is a 3-side instance where the verifier picks a random clause sends that clause to player 1, picks a random variable from that clause and sends that variable to player 2 and gets back the answer and does the test. Now this game is over like, n variable. And if you're looking at polynomial time reduction, then you can't repeat it for more than poly n times. So the number of repetition depends on the game size. And there it was important that this does not, so even if the value of the game is 0.9, it was important that to show that it decays exponentially or it decays with n. Okay, so in the remaining...
You can take more time, there were many questions.
Oh, good. So yeah, I'd be happy to, because I think I have still more than like around 1 hour. I mean, I was not trying to cover this. This would take even more, but this part itself is like 45 minutes. But just let me know when to stop. I can just stop at any point. Yes. But since you said it, I'm going to take at least 5 minutes extra. Or okay, maybe I should not. or maybe I should say this. I mean, people who want to leave after like 1 hour, feel free to. And then, okay. So yeah, so these are all about the applications of the inverse theorems that we proved, and now I think in the next 20 minutes I want to focus on the actual project, the constraint satisfaction problems and of algorithm to approximately solve constraint satisfaction problems. Okay, and so I'll start with like basic things. So there are these well-known constraint satisfaction problems. So in 3SAT, you have Boolean variables, let's say x1 to xn, taking true or false values. And you have a bunch of constraints. Each constraint is an OR of 3 literals. Okay. Think of there are like 100 times n constraints. In 3lin, the same setting, you have variables, Boolean, and then every constraint is an XOR of 3 variables being 0 or 1. It can be a k-ary predicate where every constraint is an AND of k literals, and so on. So here the goal is to assign values to the variables that satisfies all the constraints. Okay, so you want to find an assignment that satisfies all the constraints that is part of your input, or you have to decide if there exists such an assignment or not. And in max CSPs, we relax this goal. We don't expect the algorithm to satisfy all the constraints, but we just expect that the algorithm should output an assignment that satisfies as many constraints as possible. Okay. So even if the original system is not fully satisfiable, this algorithm, you're supposed to output an assignment that satisfies as many clauses as possible. So let me define max PCSPs formally. So fix a predicate P from sigma to the k to 0, 1. Again, think of sigma as some finite size alphabet, Boolean or size 10. You have a set of variables taking values from the domain sigma. And you have a bunch of constraints where every constraint is this predicate P applied to a tuple of k variables. And instead of a variable, you can have a literal, like in 3SAT, you either had a variable or a negation of a variable. And you can also define a notion of literal for non-Boolean alphabet. But let me not mention it just for the simplicity of the term. Okay. And as I said, the goal here is to find an assignment that maximizes the number of satisfied constraints. So let me just define value of an instance at sigma is the fraction of satisfied constraints, and the value of an instance is the maximum possible value, the optimum value of the instance. Okay, and the computational question here is, given such an instance of max PCSP, how accurately can we compute this value? Consider even more fine-grained question. So we want to characterize the approximation threshold for every max PCSP. So fix a predicate P and fix a parameter C, which is called the completeness parameter. So if you know that the instance is at least C satisfiable, can we find an assignment that satisfies at least S fraction of the constraints? So as an algorithm, you're trying to push this S closer to the C as possible. And as a hardness, you're trying to push this S away from the C as possible, right? So if the instance is C satisfiable, and if you have an algorithm that finds a C satisfying assignment, that's the best. You are actually finding the optimal assignment. But if you cannot do it, it's the hardness game. So as an algorithm, you're trying to push this here. As a hardness person, you're trying to push it away from C. So C is called the completeness parameter and S is called the soundness. Here, I'm asking to find an assignment. You can even consider just to distinguish between instances that are at least C satisfiable versus at most S satisfiable. Okay, So let's look at a few well-known predicates and this C and S trade-off for those. So for max 3 sat, again, the predicate is R of 3 literals. If the value of the instance is 1, if an algorithm is guaranteed to get an instance with value 1, then if the algorithm just samples a random assignment, that satisfies 7 over 8 fraction of the constraints. Okay. So if the parameter C is 1, you have an algorithm that satisfies 7 or 8 fraction of the constraints. You don't need value is equal to 1, but yes. So far so good, because the predicate is this, right? So if you sample a random assignment to X, Y, Z, there's a 7-8 chance that each constraint is satisfied, and by linear of expectation, you can actually come up with an assignment that satisfies 7 or 8 fraction of the constraints. Okay. And Hustad in his seminal work showed that that algorithm is the best that you can hope for, assuming P is not equal to NP. Okay, so the simple random assignment algorithm is sort of the best algorithm for max 3 sat. Next, consider a different predicate, max 3 lin over an abelian group, where constraints are the form X plus Y plus Z is equal to some group constant. Okay. Here, if as an algorithm you are getting an instance which is fully satisfiable, you can actually find a satisfying assignment in polymer time. Okay, so this is similar to solving a system of linear equations. Okay, so we are working over groups, but you can do Gaussian elimination sort of thing over groups also. Okay, so if the instance is satisfiable, you can find a satisfying assignment in polymer time. But what if the instance is almost satisfiable? So the best that you can get is like 99% of the clauses or constraints. Again, in this case, if you just select a random assignment, it satisfies 1 over G fraction of the constraints, and Hustad in the same work showed that that's the best algorithm for linear equations over any abelian group G. Okay, so the simple algorithms are basically the best algorithms, assuming P is not equal to NP. So let's look at a variant of this, which is the same thing, max 3 lin but over a non-abelian groups now. Okay, so fix a non-abelian group G, and every constraint in your instance looks like X dot Y dot Z is equal to some group constant. Okay. And here, the same result as in the abelian case holds when the instance is almost satisfiable. You can't do anything better than random. This was shown by Engelbrechten, Holmerin, and Russell. Okay. But if the instance is satisfiable, the situation changes from here. So you can't really do Gaussian elimination over non-abelian groups. In fact, the problem of checking satisfiability here is NP complete. Okay. And not only that, there is an algorithm which does better than the random assignment for some group. So there was a folklore algorithm which gave a 1 over size of the commutator subgroup of the G approximation algorithm, which is better than 1 over G for certain groups, because this subgroup could be of smaller size. And in 21, we showed that that's the best algorithm, assuming P is not equal to N. Okay. Okay, so if we come back to the original question, given a predicate P and given this parameter C, what is the best S that you can come up with so that there's an algorithm that outputs an assignment that satisfies S fraction of the constraints? And this question is mostly answered by Raghavendra in 28. So the result is that for every predicate and for every completeness parameter, there is a right threshold S of C, such that it's hard to find a satisfying assignment better than S of C plus epsilon for every epsilon, if the instance is C minus epsilon satisfiable. So fix C and fix any predicate. So if you give me an instance which is closer to this, whose optimal is closer to this, there is no algorithm that finds an assignment that is in this range for some S of C. Okay, that's the hardness result. And it also comes up with an algorithm. Not only that, there is an algorithm that finds an assignment of S or C if you give an instance like right at the threshold here, C. Okay, so this is like a full characterization in terms of approximation of constraint satisfaction problems. And this hardness result is assuming the unique games conjecture. Okay, so I mean, this almost answers all the questions with respect to approximation of CSPs, except for the fact that this loses perfect completeness. So this result cannot be used to answer a question like, what if I give you an instance which is fully satisfiable? Then how best can you do as an algorithmic person? Because there's always an this hardness level only applies when epsilon is some non-zero constant. So that's the main question that we study in this whole CSP project. So the main question is characterize the approximation threshold for every satisfiable CSP. So fix a predicate P, and we ask this question: if I give an instance which is fully satisfiable, what is the best assignment that you can come up with in polynomial time? And the answer will change for different predicates. Like for 3 sat, it was 7 or 8, right? But that's what we want to find for every predicate P. In other words, for a given predicate, what is the smallest S, so that we can show that it is NP hard to find a S satisfying assignment on fully satisfiable instances. Okay, as I said, for 3 sat, the threshold was 7 or 8. For this 3 lin over a non-abelian group, the threshold was 1 over size of the commutator subgroup. That's the right threshold because there's a hardness and there's an algorithm, right? So is the question clear? So that's the question that we want to study. For a general predicate, what's the right threshold? And this is a non-trivial question, even to characterize for which predicate the quantity S is less than 1. And this was the famous dichotomy conjecture, which asks basically, given a PCSP instance, is checking satisfiability of this instance NP complete, or can it be doable in polynomial time? So this is just about classifying for which predicate the soundness parameter is less than 1. And this took many years, and recently this got resolved by this amazing work by Bulatov and Zhuk. Independently, they resolved this.
Bulatov proof was rejected. There was a bug in it.
Oh,
The only correct proof I know is Zhuk.
Oh, okay. Sorry, I didn't know that fact. Okay. All right. Okay. Yeah, so this dichotomy conjecture was resolved recently, and now we know at least for which predicates the soundness is less than 1, and for which you can actually find a satisfying assignment in polynomial time. Okay. And now, since this is resolved, the next natural question is find the optimum value of S for every predicate. And yeah, and this is the central question of the CSP project. Okay. Now, I just want to motivate, I just want to go over one specific predicate, which is again what I just mentioned, which is linear equations or non-abelian groups. And that algorithm will sort of give us the idea of what direction we should look for in trying to answer this question, at least. Okay, so here it was easy, right? It's just Gaussian elimination. And now I want to focus on this algorithm here. Okay. And the main property in both these algorithms, as we'll see, is the linearity of a predicate. So let me first go over this algorithm, and then I'll go back and define this property linearity. Okay. Just a few definitions. For two group element G and H, a commutator of G and H is this element G inverse H inverse GH. A commutator subgroup is a subgroup generated by all the commutators. For example, the commutator subgroup of GL and Q, these are invertible n cross n matrices or FQ, is SL and Q, these are matrices with determinant 1. The commutator subgroup of SN, which is all permutations of size n, is AN, which is all permutations with even parity. Okay. So the only property that we'll need for the algorithm is this process called abelianization, which is if you take a quotient of any group with its commutator subgroup, then the quotient group is always an abelian group.
Yes, maybe just explain that G inverse H inverse GH is 1 if G and H commute.
Right. So let's maybe just run this whole thing for an abelian group. If G is an abelian group, then you just get an identity for everybody. So the subgroup generated by an abelian group is just identity. And this quotient is just the same group G, which is abelian because G was abelian. But if you do this process for non-abelian group, this quotient group is always an abelian group. And if you take any subgroup that contains this, you also get an abelian group. For this example, this quotient group is just a multiplicative group of FQ. And for SN, AN, it's just a Z2. Both are abelian. And the property that we'll need for the optimality of the algorithm that this is the smallest such subgroup that has this property. You can't take anything smaller than this subgroup, so is that the quotient group is an abelian group, and this will be used in the algorithm. So first of all, any questions on this? Okay, just a diagram for the quotient group. So these are like all group element, and quotient is the sets here, and then every element from the quotient group is just a coset of this subgroup. Okay, so this is the algorithm. So let H be the quotient group, which happens to be abelian. Now let's convert equations over G to equations over this group H. Okay, and here I'm considering a more elaborate version of the equation. It's not just x1 dot x2 dot x3 is equal to identity, but these are like literals. So an equation here is of the form a1 x1, a2 x2, a3 x3 is equal to identity, where a1, a2, a3 are the group constants and xi's are the variables. It also works for general case. So okay, how am I converting equations over G to equations over H? I'm just going to replace each group element with the respective element in the quotient group. Right? So each element of group belongs to some coset of GG. I'm just replacing that A1 with the respective coset. And let me rename the variables xi to yi because that's a different instance. Okay, so far so good. Now, it can be easily seen that if the original set of equations are satisfied over G, this new set of equations are also satisfied over H. Okay. But now H is an abelian group, so we can actually find a satisfying assignment over H in polynomial time. So find that. So you get a coset for each yi. Now, ultimately, to get back the assignment over G, you just sample a random element from that coset and assign it to xi. Okay, so again, yi gets a coset of gg as an assignment. To get an assignment to xi, you sample a random element from this coset and assign it to xi. So what we essentially did is that instead of like sampling a random element from G, we are sampling it from a very small zoom-in subset of G. Okay. And what is the approximation guarantee of this algorithm? So you can show that no matter what you sample from this coset and this coset, there's always an element from the third coset that will satisfy the original equation. Okay. Right, and so what is the chance that you sample that particular element for the third guy is 1 over size of the coset, which is 1 over size of the commutative circle. So yeah, I mean, I really found this algorithm pretty, like it's very simple, it's somewhat non-trivial, and it combines these two random assignment algorithm and Gaussian elimination together. And this happens to be the optimal answer for the max trivial or non-abelian groups. Okay. So any questions on the algorithm?
And here you don't need only 3 variables per equation.
Yeah, this works for k-ary predicate also. Okay, so what property got used in this algorithm? If you like look at it, then this property of like linearity, like so this predicate over this non-abelian group, it satisfies some linearity property. What is it? There's a natural map from G to the quotient group H, such that whenever XYZ they satisfy the original equation, the corresponding mapped element they satisfy some equation over this abelian group H. Okay, so for every XYZ, where X dot Y dot Z is equal to identity, the corresponding mapped element they satisfy this identity. Okay, so this is what I call a linear property of a predicate. Okay, so it's important that this H is an abelian group here. So I'm mapping this domain to some abelian group so that every satisfying assignment of a predicate, the corresponding mapped element, it satisfies one particular equation over this abelian group G. And this property got used in the previous algorithm, just because we could solve this optimally. And that's the linear property that we consider in this CSP project. That was basically the starting point. That now we can abstract it out. The abstraction is that we say a predicate has a linear property if there exists an abelian group H and 3 mappings such that whenever ABC is in the satisfying assignment, then the corresponding mapped elements, they sum up to 0. And of course, you need these mappings to be non-constant. Otherwise, you could assign everything 0 to be 0.
And you want to minimize the size of H.
No, it's no, we don't want to minimize it, but yeah, for a given predicate, you could have multiple linear embeddings, right?
You really, but I guess you want to minimize the limit size.
For that algorithm, yes, but for general predicate, we may want to use some other linear embeddings into the algorithm. Right. Okay, so if I represent the satisfying assignment of a predicate like this, this is one satisfying assignment, that's another, then that's an embedding into Z5. They sum up to 0, they sum up to 0. For concrete example, if let's say a predicate is over Sn, where the accepting tuple are 3 permutations whose composition is identity, right, quadratic many such tuples. Then if you just map it to the parity of a predicate, that satisfies a linear embedding. It's non-constant, and whenever pi1, pi2, pi3 satisfies this, the corresponding mapped bits, they sum up to 0.
What happens if I can map almost all triples to the linear?
Sorry, what?
In your condition, it's for every triple ABC in P inverse,
Right.
in the accepting assignments, you are able to map them to something that sums to 0. But what if you do it for 99% of the triples?
Yeah, so then I think I would say it won't be useful in the algorithm. Wouldn't I, at least that, because remember in the Max-Theorem and abelian group, even if you satisfy 99% of the equations, you can't do anything better than a random assignment.
Oh, I see.
So the whole point of that algorithm is that it was true for every constraint. So that's why we also require that for every triple, the corresponding thing satisfies in full. So we just want to get the power of Gaussian elimination in the algorithm. That's the main point of defining this property.
I was thinking more that if you satisfy 99% of them, that you know which ones they were, so you can just kind of ignore the other ones.
No, but maybe the instance that you get, the satisfiable instance that you get, they may use every sort of triple. The only guarantee you have on the instance is that it's satisfiable. So the satisfying assignment might use all possible things, but then you wouldn't know like which constraint is using that assignment and which constraint is not.
So suppose, okay, I'll take it offline then.
Oh.
Okay.
Okay, and for this predicate where the alphabet is 5, it's a 5-array predicate, the accepting assignments are all distinct 5 tuple. You can map it to integers by just by mapping 1 to 5 with this integer, the same mapping everywhere. Right? Because since all are distinct, you get like -2 from one, -1 from other, 0, 1, -2. This all. So this may not be a finite group.
Do you have any characterization of such predicates with linear property, like it's maybe close to some, I don't know, non-abelian?
No, we don't have such characterization. We haven't looked at that. Yeah. Okay, so since I'm almost towards the end, so let me just maybe spend one time on the final approximation algorithm. And then, yeah.
I can take 10 minutes.
I can take 10 minutes?
Yeah.
Okay. Okay, still I'll go over this algorithm and then yeah, we can maybe discuss later. So the main point of this algorithm is that how am I going to use this linearity property in the algorithm? Okay, and I did not mention this before, but the Raghavendra's characterization, the optimal algorithm is based on semi-definite program. Okay.
On what?
Semi-definite program. Okay. So given a max PCSP instance where the constraints are C1 to Cm, you can write a convex relaxation of this problem, and you can solve it optimally. Since it's a relaxation, it has a wider set of solutions than just the set of accepting assignments. Okay. And what Raghavendra does is for the algorithm is that it solves the relaxation, and this SDP formulation gives you vectors, and then somehow you round the vectors to actual Boolean Boolean alphabet or whatever the alphabet of your predicate is. Okay, so the main point is that Raghvendra uses SDP to find out the optimal algorithm for every predicate. If you don't mind losing the epsilon in the completeness. So that's the SDP algorithm. And now somehow we want to use the linear property of the predicate, right? So what can we do? So we can set up a system of linear equation over a group. So let's say a given predicate has an abelian has a linear embedding over this abelian group G. For every constraint which is over y1, yi1, yi2, yi3, we can hope that, or we can add a constraint saying that the corresponding group element they sum up to 0. So here, instead of finding an assignment over the alphabet sigma, I'm trying to find an assignment over G, and I want that assigned values to satisfy all these equations. Okay. Now I can do that, right? Because I know that my instance is fully satisfiable, right? Since the instance is fully satisfiable, and because of the linearity property of the predicate, this system is also fully satisfiable. Okay, and that's the main point, right? If it is almost satisfiable, I can't use it. If you have that property only for 9 out of 10, even then I can't hope to solve this. Okay, and what is the candidate algorithm that we came up with? We solve the SDP, and SDP gives some local set of solutions on every constraint. For every constraint, if there are like 12 possible accepting assignments, then the SDP says that, okay, you know what, just focus on these 10 assignments. You don't need to consider these remaining 2. Okay, so it gives this condition for every local thing, and somehow these local distributions are connected to each other. Okay, so SDP gives some information about what to consider for every constraint or what to exclude. Okay, so we solve the SDP and we solve the system of linear equations, and we basically try to use the information from SDP, because if SDP says that, okay, look at constraint 1 and you don't want to assign 0, 0, 0 to the variables in constraint 1. Okay, then we go back and we modify the system of linear equation to exclude that assignment from being a part of the solution. Okay. So all this you have to do it carefully.
You need inequalities also. I mean, you try to eliminate.
Right.
It's in our equations and
Right.
in our inequalities.
Right. So that's a very good question. The actual way we do it is we just right now we only know how to implement this algorithm on certain predicates, where the condition that I just mentioned, that if SDP exclude one constraint, that corresponds to some equation over this thing. Only then we can do it. But yeah, that's the right question. Otherwise, we couldn't do it. Okay. So, but the main point is that you get some information from the SDP solution, and you try to add that information into the system of linear equation. And now you solve it again. Now, this solution also would say that, okay, don't assign, let's say 1, 2, 3 to variables in constraint 1. So you go back to the SDP and say that don't assign anything to that accepting assignment. Okay, and so you keep going back and forth between these algorithms until they stabilize. Okay, so far before this work, people only tried to solve SDP, solve some linear equation, and that's it, and then just do something based on these two. They never tried to get information from this, change it. So I think this is the first time we are doing it this way. Yes.
So solving the SDP will give you like a little O1 like error, right?
Right.
Does that compound when you go back and forth, or?
You can maybe just consider that you can solve the SDP optimally, like
Okay.
with one. But yeah, that's a question that one should consider.
So there's no explicit rounding.
Sorry?
There's no explicit rounding.
No. Once they stabilize, then we will round it. Okay. So the whole point of this game is to reduce the set reduce the set of possible solutions. So Raghvendra works with an arbitrary solution to optimal solution to SDP and rounds it, but we have some more information. So we are trying to use it to reduce the feasibility or feasible solutions, right? Hoping that once we reduce it enough, maybe that algorithm is the optimal algorithm.
I missed after you update the linear system of equations, how do you update SDP and the like?
So let's say in this linear system, look at all the solutions, or look at the restriction to the variables y1, y2, y3, you would get that, out of this G cube element, it only assigns some maybe 10 times G out of G cube elements in the set of solutions, right? Then you map it back to the satisfying assignment, right? There's a linear mapping between the predicate. And then maybe one of the assignment that is excluded by the solution, it corresponds to some ABC, some satisfying assignment of the predicate. So you go to the SDP and say that, okay, in this local distribution, just don't assign it. So assign 0 to that. So you modify the local distribution corresponding. Yeah, I mean, this is very high level. You have to be a bit more delicate because, as you said, I mean, you can't solve SDP exactly. There is always a loss of epsilon, but.
And this is converging because you will have a small polynomial number of.
Exactly. Every time we do something here.
Adding.
Right.
Right.
Yeah, every time we modify this, you are reducing something, some possible solution to a constraint by 1. And there are polynomially many constraints. Every constraint can have only G cube many assignments, so it's always going down. This also is also always going down. Every time you're removing one from the support of a local distribution, and there are only polynomially many constraints, and every local distribution is supported on finitely many assignments. So every time we do this, it's converging. So in polynomial terms, they'll stabilize, and then we'll use both the SDP solution and the solutions to the system of linear equation in our rounding procedure to come up with the final assignment.
So this is, I mean, what does it depend on? Like, why don't you get stuck right at the start? Like, why do you even have these iterations?
No,
For
as
example, if your system of CSP has several random, like a planted thing with several random planted assignments,
okay.
then don't you expect to never have any iteration possible? Because locally everything is a valid assignment.
No, your question is you would never do one more round of the iteration, or?
I'm asking, like, when would you even expect to need these iterations?
The question is really when it is stuck, why does it have the rounding? I mean,
Yes.
suppose they match, they agree, they don't contradict each other.
Yeah, I mean,
No, we
in other words-
didn't see, I think, well, we need to see how rounding is
why it
used.
works, or why is this algorithm really any different from Raghavendra's algorithm?
I
It's
mean,
only different if you gain something by doing this, right? And
yes.
the question was like,
I mean, the short answer is it's helpful for three lane or abelian groups.
helpful for 3 lean, I mean, okay, if you have an instance of 3 lean, how is it helpful?
So
Then you
only
just-
SDP can't. So only SDP cannot decide between satisfiable instances of 3 lane versus non-satisfiable instances of 3 lane.
Right.
So the SDP algorithm, you can't solve the max 3 lane or abelian group, which is easy on satisfiable instances. Only using SDP, you can't solve it.
Right, but then you don't need iterations, you just.
Yeah. So there you don't need iteration, but yeah, but yes.
So is there an example where you do need it?
No, I mean, yeah, I don't think there's an example. We just work it out very abstractly.
Okay.
Yeah. The only property we use is that we need like a solution to this and a solution to this, which is compatible in this sense. Like every assignment here, which is a valid assignment in a local distribution, there's a corresponding thing in the support of this. And everything here has a corresponding thing here. And then, yeah. So again, that's a candidate algorithm. We don't know whether this is the right, yeah, that's the algorithm. What we could show is, and this part that I didn't get to, we don't have, so okay, like the Raghavendra's result, we want to show that this algorithm has some approximation guarantee on satisfiable instances. That's the algorithmic part. And then we also want to show that there's a hardness result which shows that you cannot do better than what this algorithm does. Okay. So we propose this candidate algorithm. It has some approximation guarantee for a given predicate. Now we don't really have the hardness result. Okay. But how do we justify like this is the right algorithm? We have the optimality of the gadget that goes into the hardness reduction. So in this hardness reduction, the dictatorship test is one of the main important components in this hardness reduction. And we show optimality of this algorithm by designing a dictatorship test with the correct parameters.
And this is where this correlation inequality comes.
Exactly. So this is where the correlation inequality comes. And yes,
So you're going to say anything about the, even what the structure you have?
Yeah, yes, okay, yes. Okay, so I skipped the part where the last thing that I said is that, we only show the optimality of the gadget. And to show the optimality of the gadget, we need this answer to the analytical question. Okay, so let me just flash maybe a few of those things that we saw. So the first thing is for theory predicates where the predicate is not linearly embeddable. There is no embedding into an abelian group. Suppose mu is a distribution fully supported on P inverse 1. Okay, so that's the setting, right? The main analytical question. Then we show that the only way this can be high is F, GH, they are low degree. Okay, so if there is no linear embedding, then the only way this 3-wise correlation is large is when all three of them are low degree. Okay, then you might ask, is it necessary? It is necessary. So there are examples of predicates such that you can come up with high degree functions so that this is large, and you can expect, just, yeah. So maybe just for you.
Low and high is what, constant or?
No, low and high is like n square root n, like depending on n. Yeah, so constant. So low, I would say low is if this expectation is at least epsilon, then the degree of f is correlated to a function whose degree is a function of epsilon, independent of n. Right. So yeah, so this thing requires that the distribution, the support of the distribution is not linearly embeddable, and this condition is necessary. If it is linearly embeddable, you can come up with high degree functions so that this is large. And maybe I'll just say a word about it. You just look at the abelian embedding and just come up with functions which are the characters over this abelian group G to the n. Okay, just because you are sampling from the satisfying assignment, you'll always get one here. This is the same character over the abelian group. Okay, so that's the first thing. And this we use to show that only SGPs are sort of the best algorithm for predicates with no linear embedding. So we don't really need the Gaussian elimination step that I mentioned in the candidate algorithm if the predicate does not have linear embedding. So this is what we used. And very recently we extended it to a k-ary predicate with the same property. So the only difference is a k-ary thing. If a k-ary predicate is not linearly embeddable, then the only way this is high is all of them are low degree. So I'll skip this part. Okay, what if the predicate has a linear embedding? Then these functions, if the expectation is large, and if the predicate, here we need some technical condition that is pairwise connected, that if you look at the set of accepting assignment, then every pair, this graph is connected, is a connected graph, like as a bipartite graph. Okay. Now let's look at a predicate which is pairwise connected in this way, and which is linearly embeddable into some group, but not linearly embeddable into Z. So we only, for this result, we only want the predicate to be linearly embeddable into finite groups. And you can show that based on sigma, you can restrict yourself to group of certain size. You don't need groups beyond that. Here we show that if the expectation is large, then F must look like a character over some group to the n, which is basically a collection of all the groups where it is embeddable times some low degree function. So that's the structural theorem that we have for such predicates. And this is what we use to show the optimality of the candidate algorithm, at least the gadget. Okay, and this result we also use to show the restricted AP result with the restriction 0, 1, 2. Because if you look at the restricted AP over FP, where the restriction is, the shift is from 0, 1, 3, then the predicate has these properties, pairwise connected. And finally, very recently, so here we needed some technical condition that it's not embeddable in Z. And recently we showed that you don't need that. So you just need pairwise connectedness and linearly embeddable. If you have this property, if the 3-wise correlation is large, then F is correlated to a product function times a low degree function. Again, a product function is similar to like a direct sum function. It's just a product of functions over individual coordinates. Right. And this structural theorem, we needed this one for the density Held-Stewart theorem, as well as the restricted 3AP when the restriction is only 0/1, because that predicate has only this property. It is embeddable in Z, so we could not use the previous theorem. So we needed this finer, like even stronger version of that theorem, and now we have it, and we use this theorem to show the restricted 3AP and density Held-Stewart.
How did you get rid of the Z embedding?
So the previous thing, so the way we proved it is we sort of started with this expectation, and we come to a form where the inputs are coming from some large group, and then the test is really the linearity sort of test. Okay, and that's how we got the conclusion that F must be correlated to a character. And the way we got rid of the linearity is using a completely different method. So it still uses the starting few tricks of coming to a very nicer predicate. But then after that, it completely deviates from the original proof. Yeah, so I have like 4 or 5 slides for that. So yes, I can go over it later. So right, so these are all the analytical theorems that we have so far. One where it's not linearly embeddable, then F. These are like low degree functions. The other is linearly embeddable but not Z embedding, then it looks like a character over a certain finite group. And when it is linearly embeddable, maybe in Z, then it looks like a product function.
Nice.
And these are like simple looking function, low complexity function. And the way we use it in most of the additive commutaries is we use this thing to do density increment argument. So yeah, maybe I should stop here, and yeah, if you guys are around, I can maybe say a few more things, but let me stop here.